Getting my screen queued up. Can everybody see the title slide there? Great. Okay. Yeah, so
We see it as
today,
we see the browser still, so if you want to put it into
oh,
presentation mode.
let's see. I have it, oops, I have it so that I can still see notes, honestly. So I'm not sure I can do that completely. But
Okay, oh,
hopefully
that's
it's
fine. That's
if
fine.
that's okay.
Sure.
It's is it big enough for you all? It's sorry about the browser at the top, but the whole slide should be visible. Okay. Okay, great. So, hi, thank you so much for having me. I'm excited to talk to you all about the work that I've been doing with IGSD, the Institute for Governance and Sustainable Development, in collaboration with Yang Su, who's here, and John Daniel and Gabrielle Dreyfus, who's also at the Institute for Governance and Sustainable Development. And I'm going to talk to you about the blind spots that we currently have from methane-induced warming, and hopefully show you that we can see beyond these blind spots created by CO2 equivalents, and introduce a new methane metric. So I'm going to start by just providing a little bit of a roadmap of where we're going. We're going on a metrics journey. Um, and so for those who maybe aren't fully aware, a climate metric is used to relate the emissions of greenhouse gases to globally averaged temperature change. And they're often used to set and track emissions targets as well. And so I'm going to take us on a journey to explore the ways in which common metrics create these blind spots. And we'll start with GWPs, global warming potentials, where we'll explore how they obscure warming impacts, don't tell us what emission targets are needed. And I'll then show you through our work a separate methane target that having a separate methane target is the only way to meet a climate goal. And then we'll go into GWP Starland and to talk about how that is a misleading metric and is prone to misuse. And I'll make the argument that it's unnecessary because simpler alternative metrics are available. And that simpler alternative metric is the one I'm going to talk about towards the end, this sum 44. So that's where we're going. And so GWPs, what are they? How did we get to use them? So this GWP climate metric was first introduced in around 1990 when the first IPCC report introduced this idea of global warming potentials. And in this idea, each gas is scaled according to its global warming potential relative to carbon dioxide's. And it acts like a currency exchange. It converts all greenhouse gases to this universal currency of CO2 equivalents. And we call this a single basket approach. And that's a term I'm going to be using throughout this talk. So despite having introduced this, the authors actually acknowledged that there are problems with it. And here I've got a quote from that first assessment report, and I'll just read through it quickly. It must be stressed that there is no universally accepted methodology for combining all the relevant factors into a single global warming potential for greenhouse gas emissions. In fact, there may be no single approach which will represent all the needs of policymakers. A simple approach has been adopted here to illustrate the difficulties inherent in the concept, to illustrate the importance of some of the current gaps in understanding, and to demonstrate the current range of uncertainties. However, because of the importance of greenhouse warming potentials, a preliminary evaluation is made. So despite its acknowledged problems, this approach then further became ingrained when the architects of the Kyoto Protocol leveraged the flexibility that this offered countries to treat CO2 and other greenhouse gases as interchangeable, and allowed what we call single basket trading. So there, as already has been acknowledged, there are some problems with this GWP approach. First is that carbon dioxide equivalents do not equal temperature. And this is because gases with different lifetimes, like short-lived methane and long-lived CO2, will cause warming over different timescales. And GWP is problematic because in a single CO2 equivalent amount, the relative proportions of methane and CO2 are just unspecified. So let's imagine in this plot that these red and blue temperature curves consist of the same CO2 equivalent. And this blue curve contains a lower proportion of methane and a higher proportion of CO2, representing ambitious cuts to methane. And this results in a lower near-term warming that we see here. But the red curve is the reverse. It contains the same CO2 equivalents as the blue, but has a higher proportion of methane and a lower proportion of carbon dioxide, therefore representing a more ambitious cuts to carbon dioxide instead. But one problem here is that these pathways are indistinguishable if we only understand them as CO2 equivalents. So even though these examples produce very different near-term warming levels, they both, again, contain the same CO2e. Okay, now I'm going to talk about a secondary problem, and that is that using CO2 equivalent, methane cuts come at the expense of CO2 equivalents. This single basket concept and single basket trading allows methane reductions to replace carbon dioxide. And the consequence of this is that, see, something is not animating. Okay, there we go. So the consequence of this is that there's a trade-off between near-term and long-term warming. And so I'm illustrating this with the extension of these plots over further into the future. So in the blue case, favoring cuts to methane comes at the expense of the long-term temperature goal, where we didn't do as much, we didn't make as many cuts to CO2. In the other extreme, in the red case, we favored cuts to carbon dioxide to meet our long-term goal, but we allowed too much warming in the near term. So in this way, the single basket approach makes it unclear how to meet both near-term and long-term temperature targets. So if we indeed care about limiting warming in both the short term and the long term, we need separate targets for short and long-lived pollutants. So in the work that I'm going to describe here, we ask the question, to what extent do separate targets or a multi-basket approach that separately tracks short and long-lived gases improve our ability to meet climate goals? So here we compared a single basket to multi-basket approaches in their ability to estimate the likelihood for emissions pathways to meet a near-term climate goal. And our first step in this approach was to categorize the AR6 pathways from the IPCC report into overshoot or non-overshoot categories based on a mid-century temperature goal that we put here at 1.7, while also imposing an end-of-century constraint on all the pathways. So what we should see here is the largest separation at around 2050. So with these categorized pathways, we then built logistic regression models. And I have here the math, but if the math is overwhelming for you, don't worry, you can gloss over your eyes. I will explain the basic ideas. So for a two-basket logistic regression model, the model contains carbon dioxide and methane as separate predictors. But for the single basket model, CO2 and methane are pooled into a single predictor as CO2 equivalents in the same way we've been conceptually, I've been talking about it so far. So each model then evaluates these predictors to quantify the probability of falling into this overshoot category for a given pathway. And an important aspect of this approach here is that it uses emissions metrics to evaluate the probability of an outcome. And it's not this deterministic mini model optimized to predict a specific temperature. It's really about probability. It's a probabilistic approach to the problem. So one complication of using the AR6 pathways we discovered is that carbon dioxide and methane emission trajectories in these scenarios are highly correlated. And you can see that in this, this distribution here of the correlation coefficients for these different pathways. Very, in majority of the AR6 pathways, they're like almost perfectly correlated, and the mean of correlation value is very high. And this is a problem when we're running logistic models. But so to overcome this statistically narrow set of pathways and to account for the fact that this tight correlation is not actually a natural constraint or frankly consistent with current emissions trends and policy commitments, we generated a synthetic emissions data set that covers a wider carbon dioxide and methane emission space. And you can see that in this distribution of this like sort of navy blue, what that correlation space looks like. And the average is closer to zero. The mean is closer to zero. As with the AR6 data set, we categorize our synthetic pathways based on an overshoot above some mid-century target. And then we ran logistic regression models with this larger data set. And here's just a sample of like what some of these pathways look like. There's 5,000 pathways in total, but we just showing 10 of them here. So we have the methane emissions shown here, and then we use an AGTP or what did I say? An absolute global temperature change potential to derive those warming values. Okay. So building up these classification models raised a question for us, which is which methane metric is the best predictor of methane's contribution to warming in this two basket case? What can we plug into our two basket model? And so it's already established that the cumulative sum of carbon dioxide captures its warming impact, but there's not a clear metric for methane. So we did a little mini investigation where we used the AGTP derived warming from our methane only emissions that I just showed you in the last slide. And we identified the 44-year sum, which we will call sum 44. And that's going to be the focus of the second part of this talk, but we identify it here for this purpose. And we conducted a comparable analysis with the same emissions, synthetic emissions, to identify a time horizon that represented the change in methane emissions and settled on the difference over a 20-year period so that we could focus on a near-term target. It was also a nod to GWP star, but we'll get there. Anyway, so we developed, we built these two versions of our two basket models, each containing one of these newer methane metrics that we've developed. And once we developed this metric, we selected the year for when that metric would be the most different between categories. And we did that for each of the metrics, including GWP. And you can see that indicated by this arrow here I put here, which represents the year when the ratio between group variation within group variation is maximized. So that's what we're looking at here. We're pulling out the year for this metric. So I want to take a moment to just point out one of the advantages of this two basket approach is that for this two basket, we are allowed to identify the optimal year for both metrics, and they can be different. Whereas in the single basket, we're stuck just selecting a single year for both types of gases, so in our aggregated CO2e. So that's a potentially an important difference between these approaches. So then once we built all the components of our model, we then compare performance between these different models. And what we find is across both of these data sets, the synthetic and the AR6, that the two basket model represented here in navy blue more accurately classifies pathways that meet the mid-century temperature goal compared to the single basket model here in gray. So I'll walk you through these plots a little bit. In these, we're seeing the range of warming up to the target year, so up to 2050. And what we're looking at are pathways that were misclassified by the model. So that where the model just made a mistake, didn't do it well. So these are missed detections, basically. And the dotted line here marks the temperature goal. So what that means is any shaded area above this dotted line represents pathways that exceeded the target and were misclassified as being below target. And so this means that the two-basket approach predicts a narrower range of possible warming outcomes at the mid-century target. And we see that by this narrowing here. And it predicts fewer degrees of warming both above and below the mid-century target than the single basket here in gray, which has a wider spread. And where it matters most for in a policy perspective is that it is in the level of overshoot. How high above this dotted line do these lines go, do these plots go? And we can see the level of overshoot here is reduced by a factor of 4.5 or by up to 0.08 degrees when applied to the synthetic data. But the level of overshoot is still reduced when applied to AR6, just that reduction is smaller. So we see that it's, oh, I'm hearing some kind of ringing. I don't know if that's,
Oh,
I don't know if anybody else hears that. I'm just going to keep going. I don't know if anybody else hears this ringing. It's good? Okay. Okay. Let's see, what does the chat say? Okay, great. All right. Sorry about that. If we take a closer look here, I've zoomed in to what's happening in the year 2050. We can look at the individual pathways in that target year. And as is shown in these histograms displaying the warming in 2050 for each of these misclassified pathways, we also see that the two-basket model misclassified fewer total pathways regardless of the data set. So that's in both cases. Okay, so while these results here that I've shown you indicate a robust advantage of the two-basket models in better constraining overshoot, we wanted to better understand the differences in the size of that advantage between these data sets, and particularly why the AR6 data set's a disadvantage or had a disadvantage or had a relatively smaller advantage. And I'm not going to go into the deep dives that we took in the paper to understand this, but I'm just going to summarize them very briefly here. So briefly, we found that the correlation between carbon dioxide and methane is the largest contributor to the difference in performance. We also looked at the inclusion of other gases and found that did reduce the advantage of the two-basket approach slightly, but not nearly as much as the correlation. And finally, we found that the abruptness with which methane is cut in the pathways influences the choice of which metric ends up getting used in our models. But again, like I said, I won't go into it here. I can pull up some backup slides towards the end if there are questions, but you should take a look at our paper if you would like to see more of the details. Okay, so just to summarize what this study accomplished, what I've told you, we quantified the ambiguous warming or blind spot from these single basket approaches. We provided a statistically robust set of evidence that separate methane and CO2 targets are needed to simultaneously meet long-term and near-term temperature goals. And we offer a way to set those separate targets for methane and CO2, including using a new methane metric. And here, now let's shift gears a little bit and take a closer or a deeper look at this new methane metric that I'm talking about, which we show can serve as a temperature indicator. So sum 44 is simply the sum of methane emissions in the prior 44 years. So as an example here, I show on this plot a sum 44 metric a measure in 2050 would just sum the methane emissions from 2007 until 2050. And the way that we settled on this 44 years, which may seem a little arbitrary at first, was through a sensitivity analysis. And again, I'm not going to go into all of the details, but using these same synthetic pathways that I described earlier, these 5,000 pathways, we compared methane's temperature contribution to the sum of emissions over different time frames. So starting with 10, then 20, and so on, up to 60 years. And through linear regression, some of the plots are shown here, we identified that the best fit to temperature is just for 44 years. So why are we interested in this new metric? Other metrics have been proposed and exist. And much of the metrics work has been motivated by a desire to track warming with greater accuracy. So as we can see here in this plot, the blue line represents GWP 100 for these methane emissions from this RCP 4.5. So what's wrong here? The blue line continues to increase even though temperatures start to level out and eventually decrease in response to decreasing emissions. And note that, just want to make a comment that this problem doesn't go away if we instead use GWP 20. The shape of the line will be similar, it's just scaled to be higher. So an alternate metric, GWP star, was developed to capture decreasing emissions using the emissions rate. And here I show the formula for GWP star and its two stock and flow components, which by the way use a 20-year time horizon for its flow term. If the rate of emissions is decreasing, that flow term goes negative, and that's what allows GWP star to decrease. And this is what gives GWP stars its greater accuracy in tracking temperature than traditional GWPs. However, keep in mind that there's not a strong basis from physics for this formulation, and we'll discuss some other problems with it. But with this in mind, we then ask the question, how does our sum 44 metric compare? And we find that it does pretty well for this particular RCP. But we wanted to do a more formal comparison. So we generated, again, 1,000 synthetic methane pathways spanning a wide emission space and compared GWP and sum 44 to temperature in a broader way. So what we find is that sum 44 performs comparably to GWP star as an indicator of warming. And I show that here through our linear regression results. And I just want to make a note here, a methodological note, that our synthetic pathways isolate the methane emissions and their unique warming contribution. So no other pollutants are involved here. They don't provide a confounding effect. This is just methane's contribution to warming. And so this finding is also robust if we examine each emissions pathway separately in their own linear regression. So on the left, we see that the root mean square error, which is a measure of goodness of fit, we see that for each pathway's regression is shown, and that for sum 44 here in orange, the root mean square error is lower than for GWP star in purple. And on the right, we're looking here at the difference in performance on a per pathway basis. And we can also see that sum 44 outperforms GWP star in 63.5% of pathways. So while we've shown that sum 44 performs comparably to GWP star, why are we considering this additional metric? Well, GWP star has a suite of implementation challenges, shall we say. GWP star was intended, first of all, to indicate this idea, this concept of additional warming. And this relies on an arbitrary baseline. There are no guidelines on how much historical data to include when referencing additional warming. Second, GWP star can take on a negative value even if actual warming is positive. And this can lead to the conclusion that there is a net cooling effect when in fact any emissions still cause a net warming. And additionally, we find that this baseline reframing practice can be used to distort the warming impact when applied at subglobal levels and create an equity problem. So just creating this whole different problem. So I'm going to walk us through each of these issues with some examples now. So first is the idea that GWP star's additional warming concept is misleading. So in this one study that I'm going to walk us through, methane emissions from cattle in the US are shown here. And the authors claim that using GWP star, the projected climate impacts show that methane emissions from the US cattle industry have not contributed additional warming since 1986. There's that term, additional warming. So even though US cattle populations and methane emissions have been greater than zero in all years shown here in this figure 2, the plot in figure 3 shows the warming impact as negative. And this gives the false impression that US cattle has been beneficial for the climate by causing a net cooling effect when, in fact, the presence of any emissions still causes a net warming. And so this should not be equated with reaching zero emissions. And the reason GWP star goes negative in these years is predicated on, frankly, an arbitrary decision to use 1980 as a baseline. So GWP star in 1980 is set to zero, even though the emissions in 1980 still contribute an actual positive warming amount. So on the left here, I've recreated this plot, this figure 3 plot, with a shifted y-axis that includes the historical data and shows that GWP star's actual warming in this case is still positive. And below I plot the same emissions data, but in terms of our sum 44 metric. And in contrast to GWP star, sum 44 is always positive as long as there are any emissions. And one of the nice things about sum 44 is there's no ambiguity over how much historical data should be included. All right, so finally, I'm going to talk about how this baseline reframing can also distort the warming impacts when applied at subglobal scales, and this creates unfair accounting. So imagine two farms here. This is a nice illustration from McKinsey. So imagine these two farms. On the left is a large operation with 15,000 cows. On the right is a smaller operation that is just getting started. And in year 2, the large operation makes no changes to their herd size, but the smaller operation gains 5,000 cows. So if we consider their total emissions, the larger operation has a larger warming impact. But if we consider their warming impact in terms of GWP star, this small operation gets unfairly penalized. And these types of emission changes, emission shifts, are representative of what's been happening across the global north and global south, with the global north stabilizing their cattle sizes and the south growing. So despite these opportunities for misuse, I did want to point out that GWP star is appropriate in the narrow context of, in certain narrow contexts, namely its use in the remaining carbon budget. So, keep in mind these past examples I just explained to you as I go through this list. The non-CO2 component of the remaining carbon budget is framed or provided in terms of its GWP star. And this is okay because it represents the allowable additional warming above our current warming level. So we're talking about, we are talking about a context in which additional warming, we're really actually just interested in that additional warming. It also indicates the peak warming level, not temperature, as a function of time. And it's also only applied on a global scale. The remaining carbon budget is talking about a global carbon budget. And finally, this remaining carbon budget has an assumed time frame, 2020 to 2050. And this sort of is an echo to the earlier part of the talk where short-term impacts are therefore only traded among other short-term impacts. We're not talking about long-term and short-term impacts trading off. So just to kind of bring us back to this this new metric, some of the key features of Sum 44 are its ability to forget. And Sum 44 can decrease, it has this ability to decrease like GWP star because it forgets emissions older than 44 years. And we show in our the first paper actually that this has a small effect on the warming accuracy. It also doesn't have as, and that's relevant for equity because it only captures the historical emissions that remain relevant to today's warming. Additionally, this Sum 44 metric is both additive, so it's very simple, and it's transparent because of that. So with this additive nature, it can facilitate setting and tracking methane emissions targets. And if we don't, I'm not going to go into all of that right now, but if you want to learn more about some proposed ways that could happen, we'd explain that a bit in this follow-up paper, assessing alternative methane emissions metrics conducive to quantifying global warming and setting near-term climate goals, where we elaborate on this Sum 44 metric. So to just conclude and summarize what I've told you, the first part of this talk showed that 2 climate goals require 2 separate emissions targets. A 2-basket approach will better constrain this overshoot, the magnitude of overshoot. And this Sum 44 metric can facilitate setting and tracking a methane emissions target, as we saw in that first part of the first talk when we use this probabilistic approach. This Sum 44 metric also offers a comparable temperature approximation to GWP star, but without its implementation challenges. So I walked you through the ways in which GWP star can be misleading and has been prone to misuse. And because we have alternatives, this GWP star metric really is unnecessary. So I'll close with that statement. Thank you for your attention, and please send me your questions, comments to my email. Always happy to entertain. And yeah, I'll take some questions now.